Okay, good morning, everybody. So today we're going to go into a little bit, ever so slightly more advanced machine learning algorithms. So in other words, we are now going to progress from the 50s and 60s into, well, the late 60s, early 70s. Right? So we're working our way towards, well, basically today's methods. And we'll probably take a shortcut that gets us sometime around 1990, 1995. Those older methods are still quite popular, and in some cases, they're good enough for what you want to do. So the first thing we'll do is we'll look at the perceptron. And the reason for doing this is manifold. One of them is, well, there's this interesting connection between, machine learning and the brain and all that. And if you read the news recently, you would have seen people arguing that certain machine learning architectures are like the brain, or maybe not, or maybe they are, and then some people are worried about AI and various other things. But the bottom line is, it's undeniable that people have taken a fair amount of inspiration from neural systems in order to design machine learning systems. Now, I would say all you should do is take inspiration, because airplanes don't have wings and they don't flap with them either, and well, animals don't have wheels, and still jet engines and stiff wings are actually a really good engineering idea. So just because something is solved in a specific way in nature doesn't mean that you have to build such a system on a computer, but sometimes it's a good idea to draw inspirations. So obviously this is not how the brain works. This is state of the art about, end of the, 1848. They thought that there were different areas for doing, interesting things. I mean, which to some extent is true, that you have visual cortex and so on, but it's very clearly not that map of the world like what they thought in 1848. So let's start with something very simple. So, after all, we're all learning systems. I hope that you all will get something out of this class and learn something from this class. So bottom line being, there must be a biological mechanism why this is a good idea, because, animals don't just involve learning behavior for no good reason. So the idea is essentially that, you can encode things, for instance, by your DNA. So the fact that we are humans and not houseplants has something to do with the fact that this is encoded in our DNA. But on top of that, probably something like machine learning is not in your DNA, but you may have to learn this, right? So the idea is essentially, good behavior should be rewarded, bad behavior punished or not rewarded, and this will overall improve system fitness. Now you could argue, you're sitting in this class because it's a STAR course, and therefore, you have to take it. But ultimately, I hope that it will actually help you beyond the fact that you have to do it. So, avoiding being eaten by a saber-toothed tiger should be obviously rewarded, or maybe if you even kill it. And then the other thing is, you would like to have a system that at least can infer correlations. Sometimes people are pretty bad and assume from correlation causation. So that entire measles and vaccination and autism part is a classical example where people infer from correlation causation. It's just that, the measles vaccination happens around the same time when you usually first discover autism in kids, and inferring from that vaccination causes autism is, of course, stupid, because you could just as well say turning 3 years old causes autism. But overall, this is a useful mechanism with all the logical fallacies aside. So a wonderful example is Pavlov's salivating dog. So who knows of Pavlov's dog? Okay, it's majority. Those of you who don't know, basically Pavlov took a dog, and essentially whenever he was about to feed him some food, he would ring a bell. And then, yeah, he instrumented the dog in very horrible ways to find out whether he was salivating and so on. And basically, after a while, the dog had learned the strong correlation between the bell and the food. And so just ringing the bell on its own would already cause the dog to salivate. So just like Mondays and Wednesday mornings should get you, just by their very nature, really excited about waking up early for this class, right? So we have effectively, two training mechanisms. One is, the hard coding through DNA, and that's at way longer time scales than what we usually care about. And then the successful behavioral modifications of individuals, in other words, learning. So this is about as biological as this class will get. Basically, if I look at the neuron, well, it has a CPU somewhere, which is basically taking all the signals and combining them and doing something interesting with it. And that doing something interesting with it is fairly limited. It basically, takes them, and if there's more of them coming in, possibly in a certain order, it'll start emitting some signals. But usually along the lines of more is more. Then you have a dendrite, which is essentially like, the aggregator for all the inputs, and this combines the inputs from, several other nerve cells. And then the synapse, that's exactly, where the signal goes from one neuron to another one. And you can basically store interesting weights that tell you then, whether, for instance, they're excitatory or inhibiting, and, how much they do this. This is essentially the parameter store. And then you have an axon, which is essentially like a gigantic cable. It can be like up to 1 meter long, so like 3-4 foot, and it's quite easy to understand why. Well, if I move my leg, then this information somehow has to go from my head down to my leg, and so I need a cable that transmits the signal. Well, fancy cable. But that's really all it is. So there's not too bad a reason of actually thinking of those neurons in a fairly mechanistic way. So what we're going to do is we're going to abstract a little bit away from that. And so this is a neuron like a machine learner thinks about it. I basically have some inputs and x1 through xn. They are then, transformed with some, weighted with some weights w1 through wn. And then this is all just summed up, and I get an output, and sometimes I might have a nonlinearity on top of that. Okay. This is by and large what all neural networks do. This is also what a lot of other linear and nonlinear classifiers do. So this very primitive, simple observation, okay, w.x plus maybe some offset b and some nonlinearity on top of that, that's really all that we have. So I might have something like, some function g of all of this, right? And then one of the more recent progresses that were made in deep networks was to use as this function g, this function. I'll just draw it. Okay. This function here. This is sometimes referred to as ReLU, rectified linear units. Okay? So that should tell you that actually the basic ingredients are not rocket science. But you need a big computer and a lot of patience. Okay, now, if we have this weighted linear combination, we can actually, then do something useful with them, right? So, for instance, if I want to learn linear separating hyperplanes, I can use that to separate ham from spam, so basically good from bad emails. I can maybe infer whether some observations are novel, or I can figure out whether a user is likely to click on an ad or not. So, matter of fact, all those things in many, many systems that are deployed that you're probably using rely more or less on a fairly simple linear classifier. So, for instance, the decision which ad you're going to see if you go to, I don't know, CNN.com will probably be driven by some very gigantic linear classifier that sits inside one of the add exchanges, and yeah, will do interesting things for you. And then, of course, you know how much I bid for it. Okay. So learning, in this case, is quite simply, well, let's learn the coefficients W and B. So W are basically these terms here. And then B is simply, you know, this additional input plus B. Sometimes also called a bias. We already dealt with a bias before a little bit, where I said, well, you know, for a linear function, let's just incorporate the bias as just yet another feature, which is a constant feature then with some weight. And that's about it. Okay, so let's see what we can do with that. So let's say I have ham and spam, and I want to separate ham from spam. Then actually pretty much any of those linear separators will do the trick, right? And so as long as I can find one of them, I'm fine. Just quick question. Which of those separators do you think looks best? Who votes for the red one? Okay. So we have 0 votes for the red one. How many votes do we get for the purple one? Okay. 0. How many votes do we get for the green one? Almost everybody. Almost everybody. Who votes for the black one? Nobody. Okay, good. Why did everybody vote for the green one? I mean, yes, it looks pretty and green is a nice color, but why? Okay. Correct. So this is something like a maximum margin classifier. I'm not entirely sure this actually truly is the maximum margin classifier, but among all those linear separators that we saw here, it probably has something close to the maximum margin. I mean, if you squint hard, you would probably pick something that's very close to the green one, maybe something like that. That might have the maximum margin, if I could draw a straight line. Okay. So your intuition is pretty good. We will actually get to that in probably about 1.5 lectures from now. But so for the moment, we'll just content ourselves with even trying to find any of those separators. Quick check on intuition. If I, you know, let's say I was going to add some more points, right? Maybe I'll add another point here, another one there, another one there. So did I just make the problem harder or easier? Who thinks I made the problem easier? Okay. Who thinks I made it harder? Okay. The rest isn't quite sure yet. Well, the reason for thinking it's possibly easier is because now I don't have so many different things to choose from, right? So, you know, there's basically only really 1 or 2 separators that could really take care of this, right? So, in other words, among my hypotheses, there is a much smaller set. But that actually usually turns out to make the problem harder, especially if I have a randomized algorithm and I'm basically throwing darts at my solution space. So if my solution space is smaller, it's harder to find the right thing. So your intuition was correct. This made the problem harder. And we'll actually see this in math. But I just wanted to make sure that we sort of kind of get the idea before that. And yeah, that's apparently how people showed up in the office in the 60s, or at least when they had pictures taken. So this is Rosenblatt and this is Widom, and they were some of the first ones to actually build a perceptron. Okay, and they actually did some math for it as well. Yeah. So let me give you the algorithm right away, because it's a very simple algorithm, and then we're going to go and analyze it. And yes, I'm sorry, there's some math ahead of us, but it's not very difficult math. And it's, in a way, the prototype of the kind of algorithms that we will see a lot. So stochastic gradient descent algorithms have that flavor. So what I do is I start with, w equals 0 and b equals 0, because I really don't know what my separator should be. I don't know what my offsets should be. So I could just start with w0 and b equals 0. If I had some idea of where to find it, I might not do this. I might pick another w and b, right? So if I have a good guess of what separates it, well, by all means, start out with that. And then the algorithm is actually very simple. All I do is I just check whether the points lie on the correct side of the hyperplane. So that's this condition here. Okay, so let's check actually what happens. So let's assume that y equals 1. What this condition means is, well, w dot x plus b. If this is less equal than 0, that means I have made a mistake, right? So in other words, if I make a mistake, then perform some updates. Let's look at the updates in a moment. If y equals minus 1, then what I need to do is I need to check whether w dot x plus b is greater or equal than 0, right? But that's the same thing as multiplying it by y and replacing this again by less equal than 0, right? And of course, if y was 1, I didn't have to do anything terribly difficult either. So that's why this condition, this one here, actually automatically checks whether things are on the right side of the margin. Okay. Now, if this happens, then I perform the following update. W goes into w plus xi times yi. So, in other words, I'm adding my observation to my weight vector. So it's just like, whenever the dog hears the bell, and afterwards, he happily sees the meat, he just adds the bell to the weight vector. And so, of course, if this over here is the bell, okay, I'm going to draw a horrible bell, and this is my weight vector, then it keeps on moving in that direction, right? And so, of course, now if I see a new bell, these two things align very well, and I get the happy dog. Now, what I also do is I offset the bias, basically such that b goes into b plus yi. So if y was positive, then, and I didn't get it right, then I shifted the entire function a little bit more towards positive numbers. Okay. And I just keep on doing this until everything is classified correctly. So this is about as simple an algorithm as you can imagine. You can write this in 4 lines of MATLAB. This wouldn't necessarily be the world's most efficient implementation of it, but it would do the trick. So, you can teach that to an undergrad and they'll get it and they'll implement it and it'll work. So a couple of interesting observations there. Nothing happens whenever I get things right. Basically, if I'm already classifying correctly, no need to update, I have to do no work at all. So in other words, I'm only learning whenever I'm making a mistake. Which is, by the way, a reason why you should actually look at the annotations of your homework, right? Why you should look at the correct solutions. Because this is going to give you a really useful feedback signal to find out when you're getting things wrong and when you're getting them right. So here's the mathematical or the algorithmic reason for looking at your corrected homework. Secondly, the weight vector is a linear combination, right? So in other words, what we're getting in the end is w equals sum over yi xi. And what that means is that the classifier is again a linear combination of inner products between the data and some of the previous instances. Right. Now this looks like a ridiculously inefficient way of coding things up, right? Because if I'm living maybe in a 100-dimensional space and I am seeing 1,000 updates, so basically my set I has has cardinality 1000. Then writing things out in terms of 1000 in the products here seems like about the worst possible thing that you could do. Right? That's true if I'm in a very low-dimensional setting. It turns out that if I'm in a very high-dimensional setting, this is actually a really, really good idea. So we will actually see that this very trick will let us to do nonlinear separators very easily without really having to do much work. Okay. Any questions so far? Is everybody cool with the updates of the Perceptron algorithm? I mean, it's like a super simple algorithm, but I just want to make sure that everybody's cool with that. Because now we're going to do some math. So the celebrated convergence theorem of Rosenblatt, one of the guys on the picture before, is that if there exists some solution x star w star with unit length, and for which the data is properly separated by some margin rho, then the perceptron converges to a linear separator after a number of steps, which is basically b squared r squared over rho squared. And that plus 1 and so on has a lot to do with just the fact that we have a constant offset. If you didn't have that, it would be basically r squared over rho squared. That's really the interesting quantity here. So what this does is it confirms what we saw before in pictures, right? Before I asked you, which of those separators is which of those problems is easy. And as I made the gap between, the positive and negative set smaller, of course that margin gets smaller. So if rho gets small, then 1 over rho gets large, and so therefore I need more iterations. So the algorithm will make a lot more mistakes until I finally find the right thing. So this theorem does not tell you how much data you need to see. It only gives you an upper bound on how many mistakes you're going to make. So the most desirable thing would be to make all the mistakes right in the beginning such that afterwards you get everything right. In other words, fail fast. The cool thing is this is dimensionality independent. So I could have picked, a ridiculously high dimensional problem. It still would have been okay. It's also independent of the order in which I'm seeing the observations. So I could have an adversary ordering them in the most evil way for me, and I still get that guarantee. And as we already saw, it scales with the difficulty of the problem. So this is a very, very nice convergence theorem, and you can use this to design a lot of interesting algorithms, including semi-definite programming and so on from that. So in other words, it's actually an algorithm which solves a feasibility problem. Because what I'm doing is I'm trying to find some linear function such that this linear function satisfies a whole bunch of constraints. And essentially what this does is the perceptron algorithm gives you a method for finding a feasible solution to, a set of constraints very quickly. And as you would expect, if the set of feasible solutions is really large, the algorithm finds it rapidly. If the set is very tiny, then it can take a long time. Any questions about the theorem so far? Yes?
Can it detect if it's determinate?
Can it detect whether whether a solution exists? Unfortunately, no. So there are other tools by which you can find out whether such a solution exists, but that usually then requires slightly more interesting quadratic programming techniques or linear programming, and then you can check whether, for instance, the dual of that problem is unbounded and things like that. So there are specialized algorithms that can help you detect feasibility quicker, but usually a proof of infeasibility requires that you look at something called the dual. Now, you've probably not done a lot of constrained optimization yet. We are going to cover that in a fair amount of detail after that block, so after unit 4, we will basically catch up on the rest of optimization that was not covered in the recitations yet. Okay. So I assume that everybody is attending the recitations. They're actually required for you as background if you don't know the stuff yet. We'll need it in the main class. Okay. Very good question. Any other questions so far? Okay. So let's actually prove it. And so the way how we're going to prove it is actually in 2 stages. So one part of the proof basically shows that the alignment between W and B and W star and B star, so this thing here, that this actually increases linearly. So in other words, if this is my, W star, that the inner product with, W1, W2, W3, W4, and so on, that this thing here increases linearly. So that means, those 2 vectors will at some point become approximately collinear. Okay. And so, of course, the hope is that by pointing into the same direction, I will actually get a proper separator. Okay. The second part of the proof is to bound the rate of growth in the length of this Wi, basically in terms of these green guys. And then I can use those 2 parts to obtain a contradiction, right? Because I have, in one case, the 2 vectors becoming more and more aligned. In the other case, I have an upper bound on how rapidly the length can grow. And at the point where I have a contradiction, I know no further updates are possible. It must be done, because there cannot be any other pair that will actually increase the alignment and while not letting the length of the vector increase too much. Right? And so once I have a contradiction, I know there is no more update, so I know I'm done. It's actually kind of a nifty proof by having those 2 bounds that at some point lead to a contradiction. This is a very useful proof technique overall. Okay. And this is very, very elementary math. I mean, you could do this literally in high school. The concept is super cool, but the math itself is very simple. So for convenience, I'm, using subscript I to, have an iteration counter. So W1, B1 is 0. Okay, so initially this is 0. Now, let's assume I go from J to J plus 1. And I know what happened because I know that Wj plus 1 is Wj plus Yj xj. Right? Same thing for Bj plus 1. So I can actually go and write it out accordingly. Right? It's basically, Wj plus Yi times xi plus 1 and 1. Actually, this should be a j here, right? Okay. And now, this is just the old alignment. That's what we had before. Plus this term here. However, I know that the optimal solution, so W star and B star, have to be such that they actually separate the data by at least a margin rho. Right? And so I just get that this new alignment is the old alignment plus rho. And since I started with W and B being 0, I know that this has to be greater or equal than j times rho. Right? So this shows that the alignment has to increase at least linearly. The length of this vector xi and of bi, these things may increase in some way that I am not really controlling yet, but at least I know that the alignment has to increase linearly. Okay. Is everybody cool with that first part of the derivation? It's really just plugging in the updates and exploiting the condition that we had, right? This is the key part where we're exploiting our assumption. And this is where we just plugged in the updates. Okay? Good. Let's move on. Now, the next thing I need to do is, bound the length. So, okay. Actually, one thing that I also need to do is just, bound, that inner product. Okay. Now, and that's fairly straightforward. Because that's really just, this condition here. We know that W star is of length 1, B star is of whatever length that it has, right? And so the inner product between those two terms is just, some constant times the length of Wj plus 1, Bj plus 1, right? This is really just Cauchy-Schwarz. Okay, so everybody's okay with that part? Any questions so far?
Where's that constant coming from?
Where's what coming?
The constant one.
The constant 1, that's because I assumed that W star equals 1. So therefore, the length of W star, comma B star squared is 1 plus B star squared. And so that's where this is coming from, right? And then Cauchy-Schwarz, I guess everybody knows that part. So now, the next thing is we need to get an upper bound on how rapidly Wj and Bj can grow. So again, let's plug in the definition. So if we make a mistake, well, Wj plus 1, Bj plus 1 is the original term plus the update. So this is just plugging in our algorithm. And now, it's just expanding terms, just because we have a sum. So we have, the original length plus a new term here. This is, as we know, this is basically, r squared plus 1, because the length of xi is less than r. And then, last, I have this term here, which is an inner product. But I know that this is less than 0 because I made a mistake. Because that's exactly 2 times the value of, the decision function. Okay? So since this is less equal than 0, I can leave it out, and I just get the first and the third term, which is then bounded by, basically the previous term, plus r squared plus 1. So therefore, by induction, I get this. Okay. So therefore, taking square roots, I now have a lower and an upper bound on those two terms, right? The lower bound, I know that this is, less equal than j times rho. Okay, because that was from the previous slide. And I have an upper bound from here. Right? And so since I have an upper and a lower bound on this quantity here, all I have to do is I just have to now solve for j. Basically, I just divide by square root j. And this gives me the condition when this inequality can no further tighten up. Right? Because I have a lower bound that increases linearly. I have an upper bound that increases with the square root. Right? And so once the corresponding scaling coefficients, namely rho and r squared plus 1, b squared plus 1, once they collide, things have to, there's no other way to go. So think of it this way. Here we have a linear function, right? Well, it should have gone through the origin, but yeah. And here I have a function that increases like the square root. And so at some point, namely here, those two inequalities collide. And this is exactly the point where I can make no further updates. And so if we just solve for j, then we're done. Okay. I know this was a fairly dense amount of math. Actually, each of the individual steps wasn't very hard, right? I mean, you could have done that in first year after taking a linear algebra class, right? There's nothing really special in there. I mean, we just took inner products, looked at norms, and then looked at the scaling behavior by getting upper and lower bounds on the length of W and B. Right? So technically, there's nothing there, but conceptually, it's non-trivial. Any questions?
Yes.
Yes.
The WI, so at each step you update the WI.
Correct.
But there is no guarantee that each WI has normal form.
Oh, no, absolutely not.
But
So,
why did it, like, you assume that the final answer is
okay.
finally the W star is,
Okay.
has normal.
Okay. Oh, thanks for asking this question. And okay, so let me clarify some things. So I'm assuming that there exists some W star and B star that will actually nicely separate the problem, right? So, with unit length. Now, obviously, if I was to multiply W star and B star by, let's say, 42, right? Then this inequality will still hold, right? So in other words, 42 times W star and 42 times B star will also be a valid solution. So I have a certain scaling freedom in my choice of W and B. And what that means is that Wi and Bi will not converge to B star and W star, right? They will just become more and more aligned with it, but they will not converge to it. So in the limit, they would point in more or less the general direction of W star and B star. And they will be more aligned if the problem is really hard to solve, because then there's only a small, polytope around W star and B star that lets me solve things. Whereas if the problem is really easy, then there's a huge half space, and it'll just point somewhere in this half space.
Okay, so it didn't really
So,
converge to W star.
no, it does not converge to W star and B star. No. It will just become more aligned. And the point is, I'm not trying to find an optimal solution. I'm just trying to find a solution that's good enough. This is an important difference to what you usually otherwise do when you solve an optimization problem. You're trying to find the best thing. Here I'm just trying to find something that's good enough. And that's also because, well, I have, an adversarial guarantee in this case. Okay. So now let's get back to the feasibility issue. So this is exactly what I alluded to in the first lecture when I briefly mentioned black and white. So this was this computer game where basically your avatar, like this creature here, was being trained based on, whatever your behavior in the game was. And it just turned out that most likely there was no actually feasible solution for this, or at least that most humans do not behave in a fully consistent manner regarding, well, the parameterization that the game developers used in that game. So in other words, there were actually errors in this, and whenever you took an action and the avatar didn't quite, wouldn't have quite agreed with it, it did an update, and it became incredibly difficult to train this thing in the end, because every update increased the length of the weight vector, and the entire thing became very unstable. That actually pretty much killed that game. So while the good thing is that you only need to store the errors, because everything that you get right, you don't really have to remember anyway. But it also means that on noisy data, this is a spectacular failure. So now, if you think about it, this actually is very similar to what you would do for stochastic gradient descent on a hinge loss. You would basically, and we'll explain stochastic gradient descent in a moment. Basically, you have an objective function, and the gradients are either 0 or 1, and when the gradient is 1, it just means you do an update. If it's 0, you don't do an update. Okay. So this is what we already saw before. This is a hard problem, right? Because there isn't really much space where I could have picked a different W, right? I mean, this one here might just barely do it, but it's really hard. Whereas there, it's ridiculously easy to find all sorts of different separators, and they'll all be okay, right? So I don't have to work very hard to actually find something. Mind you, I could even pick something like this, and it would still be valid, right? Okay, if it was a straight line, that is. Yep. So let's look at it in practice. So here's some data, and I basically, see one observation, and this is now my separator. So the separating boundary would be probably, somewhere there, not quite clear. Whatever MATLAB's color coding is. So I observe a second point, namely this guy here, and now this is all twisted around because before that, we were pointing in this direction. But since I have this observation here, now my decision boundary gets directed quite a bit more. And here's another point that I'm adding so that, sort of kind of tilts it back. And the next one is fine, and I keep on doing this. And so what you can see is that eventually it'll be okay. Right? Yeah. So it's a very, very simple algorithm. It's also ridiculously boring, right? Because after all, the only thing I get out of this is a linear classifier. Well, I would have probably wanted to get something a little bit fancier. Right? Any questions so far? Okay. Yes?
What's the green dot?
The green dot in each case is basically the new observation that I'm seeing. Okay, so if you were to go back, it's this guy here. If I'm there, it's this term there. And basically, whenever I'm seeing a new green dot, it means I'm making a new mistake. And that changes my decision boundary a little bit. Yes?
What is the gradient showing?
Well, that's basically just color-coded for the linear. It's basically just, pseudo-color plot of, the linear function. So it would probably have its normal vector somewhere here, and that's somewhere where the decision boundary might be. Right? And so what you can also observe is that as you observe more data, the gradient becomes increasingly steeper. So initially we have this, right? And that gap will get smaller and smaller as we, get more data, because the absolute value of Wi increases. So that's why the transitions will be sharper. Yes?
When noise, you mean this fails when there's noise?
Exactly.
That, when the data is not linearly separable?
Exactly. Well, no, this data is linearly separable, right? I mean, if you squint hard, you'll see that, well, this is a perfectly good separator. But it just means that it hasn't found anything that, perfectly separates the data yet. So whenever I'm seeing an observation that I previously got wrong, well, then I'll have to do an update.
So what happens in the case of noise?
What happens when there is noise? Well, I may end up with an infeasible constraint problem. And in that case, if you're selling a computer game, you will go bankrupt. If you run this on your computer, the algorithm will never terminate, and you'll be very frustrated. And this is exactly why you will need a lot of other tools to address this. So, for instance, in the assignment, you will actually have fun with a margin perceptron, where we will then add an L2 margin to get a good solution. And this basically means that you will be able to recycle your simple perceptron algorithm and only modify it ever so slightly to get a good answer. So that's precisely why we will be doing this. Okay. Any other questions? Okay. Cameraman, if you could please stop the camera. And we will then move on to nonlinearities.